Okay, continue from last lecture. We were on the topic of metal activity series, and we discussed um, the type of single replacement reaction, where zinc as a metal can go into a solution containing copper ion and reacting with the solution turn itself into a positive ion into the solution, while throw copper out as a free element metal. Okay, and we know that this reaction does happen, while the reverse reaction, if you put copper metal into a zinc solution, okay, copper won't be dissolved and you won't be able to get zinc metal, and nothing happens, no reaction. Okay, so in this sense, we say that zinc is more active than copper. Okay, and of course, once people realize that between metals, one metal can do this to another, then people start to think, yeah, does this only happen between zinc and copper? Does it happen between other elements? Yeah. And then people start to experiment on this. Okay, I'm going to try to put all kinds of different metals into all kinds of different solutions and observe salt solutions and observe, see whether something happens too. Now, for example, when you put copper into a zinc solution, nothing happens. But then people find out, if I put solid copper into a silver nitrate solution, okay, so copper into a clear colorless solution, silver nitrate is colorless, and little by little people observe that the solution is turning green. Okay, copper nitrate is having this bluish green color, and you would actually have silver metals precipitating out of the solution. Okay. Oh, okay, so copper is more active than silver. Okay. And then one after another, people start to discover tons of single replacement reactions. And it always happened this way. Between two metals, one metal can do it to the other. It can go to the other metal's salt solution, take its place, and kick that metal out. And the reverse reaction never happens. Okay? And then little by little, so now, instead of saying zinc is more active than copper, you can simply say, well, activity-wise, zinc is greater than copper. And here you got, copper is greater than silver. Okay? And eventually, the more metals we test with, this list goes longer and longer. Okay? So, in the end, people discover this long series of activity comparison between different metals, and it kind of goes like this. cesium is the most active metal on the periodic table. More active than rubidium, more active than potassium, more active than barium, more active than strontium, more active than calcium, more active than sodium, more active than magnesium, more active than aluminum, more active than manganese, more active than zinc, more active than chromium, more active than iron, more active than cadmium, more active than cobalt, more active than tin, more active than lead, more active than hydrogen, more active than copper, more active than silver, more active than mercury, more active than gold. Yeah. So this list here now, can other metals be also included in this metal activity series? Now, yes, it could. Okay, but these are probably the most common metals that people deal with. Okay, and now you don't have to memorize this list. There's no reason to do that. Okay, but you got to understand from left side to right side, from this end to this end, this shows you, okay, how active a metal is. Okay, now, and there's another way to express this, calling it activity series. Okay, now, because if you look at this, metals in this process, okay, is this, the free element metal that you put into a solution is reacting in a way that it loses electron, turns itself into a cation. Okay, losing electron involves means oxidation process. Oxidation process means reducing agent. Okay, so you can also say, now, this is the reducing ability order of different metals. Okay, who wants to lose electron more? Elements on this end, okay, tends to want to lose electrons more than elements on this end. Okay, and that's why they're more active. Okay, cesium, it's almost like a ton of different things could make this cesium losing. You put it together with chlorine, you put it together with water, you put it together with almost all kinds of molecular compounds can make cesium losing its electron. Okay, cesium has the highest activity of all metals. Okay, while on the other end, gold, okay, is one of the least active metals. Part of the reasons why people use gold, okay, for in human history, okay, for representation of wealth, okay, because it's very inactive, it doesn't easily go away. Now imagine, okay, if gold can easily rust and disappear, who's going to count gold as money? Okay, so this is the order of activity between metals. And now you may also notice that you have hydrogen in here. Hydrogen is not even a metal. What are you involving hydrogen in here for? Okay, hydrogen in here, now remember, hydrogen is not a metal, but hydrogen is indeed in group 1A. Okay, it's in the first column of the periodic table, okay? And single replacement reaction also involve chemical reactions containing hydrogen ions. Here's the example. Zinc, when you put zinc metal into a acid solution, okay, aqueous, okay, a single replacement reaction actually would happen. You would see zinc turns into an ion, dissolve in the solution, and you would actually see gas bubbles coming out of the solution, and that would be hydrogen gas. Okay, so if you compare this reaction here with the reaction of zinc with copper sulfate, they are kind of the same type of reaction. Okay, it's all zinc going into a solution containing a particular positive ion, and the result is zinc dissolves and it kicked that particular positive ion out of the solution in the form of a free element. For copper's case, it's a metal. For hydrogen's case, it's some gas bubbles. Okay, and with the position here, you also know, okay, that everybody up front, everybody before hydrogen, so all of these guys, okay, if you put them into an acid solution, because all of these guys are more active than hydrogen, okay, you will see gas bubbles if you put them into acid. So all of these metals react with acid. What about these four guys that we put behind hydrogen? This means hydrogen is more active than these guys. So for this bunch, no reaction with acid. Okay, you're not going to produce hydrogen gas if you put these metals into an acidic solution. Okay, all the other ones up front before hydrogen can do that. Okay, now, so this is what metal activity series is. Now, what do you want me to really know about metal activity series? I understand what you're saying, but let's be straight. How are you going to test us on metal activity series? There's essentially two different ways of me testing you on metal activity series. Okay, and that's number one. Oh, change color. Gave activity series. Predict chemical reactions. What do you mean? Well, let me give you an example. Okay, let's say I know that aluminum is more active than zinc, which is more active than cobalt, which is more active than copper, and which is more active than silver. Okay, then I can ask you, okay, let's say I provide you with this portion of activity series. Okay, then I could ask you, well, does this chemical reaction happen? Would you have a single replacement reaction between aluminum metal and a zinc salt? Okay, the answer is absolutely. You're going to end up with zinc metal and a aluminum salt. Okay, this reaction will happen. Why? Because aluminum is more active than zinc. That means aluminum can go into zinc's house and kick zinc out, take its place. Okay, and then, okay, could this reaction happen? And again, same logic. Zinc is more active than silver. Okay, so zinc could go to silver's house and kick silver out and take its place. Okay, but if I ask you, would this reaction happen if I put some solid copper into a cobalt solution? Do I get cobalt and copper sulfate aqueous? Then the answer here is no. No reaction here. Why? Because cobalt is more active than copper. That means copper won't be able to go to cobalt's house and kick cobalt out and took its place and take its place. Okay? Less active metals won't be able to do this to more active metals salt solution. Okay, the more active metal could do this to a less active metal salt. All right, so if you're given a set of solubility rules, if you're given a set of activity series, you should be able to predict whether a chemical reaction happens. Okay, yeah. And then the other way around. Given reaction information, predict activity series. Well, what do you mean by this? Well, let me show you something. Now, if we know that manganese, when it put into a magnesium chloride solution, okay, a chemical reaction will not happen. Okay, then we also know that when manganese put into a iron solution, a reaction happens and it gave me iron solid and manganese nitrate. Okay, now, and let's say we also know that when lead is put into the same iron salt solution, no reaction would happen. Given reaction information, I want you to predict the activity series between the metals involved: manganese, magnesium, iron, and lead. How would you do that? Well, manganese cannot do it to magnesium. What does that mean? Magnesium must be the more active one. Okay, because if manganese is the more active one, this reaction will happen. Okay, you're gonna have solid magnesium comes out of the solution. Okay, but no reaction, that means magnesium is more active than manganese. This reaction does happen. That means manganese is also more active, okay, than iron. Okay, and then this reaction don't happen, and that means lead is iron, sorry. Is more active than lead. Well, you put these information together, what do you see? Magnesium is more active than manganese, which is also more expensive more active than iron, and then it's also more active than lead. So based on these three reaction information, whether you have a reaction or not, I can figure out an individual set of activity series for the metals involved. As long as you can do these two things, you got nothing to worry about, metal activity series. Okay, now, I can give you activity series, ask you to predict a reaction. I can give you reaction information and ask you to predict the activity series. Metal activity series was found first, okay? But once people discovered and experimented and found the complete set of metal activity series, then people start to think, well, metals can do this, and metals have reducing ability to lose electron, and nonmetals tend to gain electron and make negative ions, and we call that the reduction process, and we also call whoever involved in the reduction process the oxidizing agent. So if metals have different reducing ability, activity, does nonmetals have a activity series? No. The answer is yes, absolutely. Okay, now, very similarly, okay, metals can have single replacement reaction as well. Now, in our class at Chem 115, okay, I'm not going to add too many nonmetals. I'm not going to try to give you an activity series that cover all the nonmetal free elements. Okay. Actually, in Chem 115, our focus is on one group of nonmetals, and that's focusing on halogen group. What is the halogen group? Fluorine, chlorine, bromine, iodine. Okay. And if you're wondering why didn't you involve the next one in that group, astatine is a radioactive element. Okay. The naturally existing isotope of astatine is radioactive. We don't deal with it in chemistry that much, okay, so that's why we're not including it here. Now, but if you're only involving this group, what is the activity series between these guys? Well, let's make it clear here. When it comes to free elements activity, okay, fluorine is more active than chlorine gas, chlorine is more active than bromine, and bromine is more active than iodine. Okay, but this time, this activity series, this non-metal activity, unlike the metal activity, which is all about a reducing ability. Non-metal activity is equivalent to oxidizing ability. So what we're saying here is that fluorine is a much better oxidizing agent than chlorine. Chlorine is a better oxidizing agent than bromine. And bromine is a better oxidizing agent than iodine. Okay. Now, since this particular non-metal activity series involving only the halogen group is very simple and very straightforward. See, it's going from top to bottom in that group, okay? And the activity between the nonmetals decrease as you go down the column. So for only 4 nonmetals involved in our version of the non-metal activity series, I don't think I'm asking too much for you to remember, okay, this activity series. And now, what demonstrates the activity series between these non-metal free elements? Well, here's an example. If you put fluorine gas into a solution containing chloride ion, okay, you would see that your fluorine is going to turn into ions, okay, while kicking chlorine gas bubbles out of the solution. Again, single replacement reaction. Now, fluorine can do this too. If you have NaBr, same result. If you have NaI, same result. Okay, so fluorine can do this to everybody else. Now, when it comes to chlorine, chlorine can do it the same thing fluorine did, okay, to the 2 elements that's lower than it on the non-metal activity series. So chlorine can go into a solution containing bromide ion or iodide ion and kick them out. But if you put chlorine into a solution containing, let's say, potassium fluoride, okay, are you going to have a chemical reaction? The answer is a firm no. Okay, fluorine can do this to chlorine, go into his house and kick him out, okay, because fluorine is more active. Chlorine will never be able to do that to fluorine because, again, fluorine is the more active one. Fluorine wants to gain electron more, okay, so when it comes to competing on that, your chlorine is not going to win. No. So chlorine can only do it to bromine and iodine. Bromine can only do it to iodine, but won't be able to do it to fluorine and chlorine. Okay, and then, of course, in the end, poor iodine. Everybody else can do it to him, can go to his house, a solution containing iodide ion, and take his place and kick the iodine out. No. So that's the non-metal activity series. And really, if you put the way that we handle metal activity series here, you can see that I only actually have one type of way to test you on this. Okay, for the metal activity series, I say I can go both ways. Okay, but for the non-metal activity series, since I already asked you to remember your activity series, then the only thing I can ask you is for example, which one of the following single replacement reaction will happen between halogen group elements. So if I gave you this, you know a reaction is going to happen. If I gave you this, you know no reaction would be happening because chlorine is less active than fluorine. No. So as long as you can answer this type of question, you're absolutely fine. So activity series and the single replacement reactions are not hard concepts, and compared to the possible questions that you would be facing in an exam, compared to the balancing redox equation, figuring out oxidizing agent, reducing agent, compared to those, this is actually very easy and very straightforward concepts. All right, now so this here concludes the non-metal activity series. Okay, the end of non-metal activity series concludes our talk about redox. Okay, remember, single replacement reaction, every single one of them are redox reactions. Double displacement reaction will never be a redox reaction. Okay? Because in double displacement reaction, you have positive ions and negative ions exchange partners. During that process, your positive ion is still positive ion. Your negative ion is still negative ion. Okay? You didn't have any electrons transfer between them from one species to another. And if you don't have that, you're not redox. But on the other hand, every single replacement reaction involves metal turns into ion, a free element turns into ion, or ion turns into free element. And that's the process of gaining and losing electrons. And because it involves gaining and losing electrons, it's always a redox. All right, so once we complete this part of redox reaction, and actually you can view redox reaction part, the redox piece, chapter, however you want to call it, as part of solution chemistry. Because remember, majority of those, including our example of redox reactions, are happen in an aqueous solution. Okay, so redox is also viewed as part of solution chemistry, but it's obviously all conceptual stuff with no calculations. Anything close to, but the one part that makes answering a redox question, okay, activity series question, shouldn't be hard for anybody at all once you understand what's going on there. Okay, but balancing redox equation questions, okay, are long, and we have fixed steps of doing them. Now, you really, really, really want to practice and get yourself very, very familiar with that process. Okay, because not only you want to do it right for balancing redox reaction type of question, you also want to make sure you do it right. Okay, do it not only you want to do it, you also need to make sure you do it fast, because you can't afford to spend 15 minutes on a balancing redox equation problem on your next exam. All right, so the next thing we're going to do here, we're going to start a new chapter, and new portion of Chem 115 content, and I'm going to try to talk about energy in chemistry and chemical energy. Okay, now, first of all, the energy that we deal with in everyday life can be put into two different categories. There's the kinetic energy, Ke, okay, and what is kinetic energy? This is energy of motion. Okay. Any object with a mass and velocity or speed will have energy of motion, will have kinetic energy. Okay. Now, and some of the kinetic energy form, it's easy for us to see. Okay, a car driving fast on the highway. Okay, you obviously see a lot of kinetic energy. Higher, large mass of the car, and fairly fast speed. Okay, a lot of energy of motion is packed in a moving car. Okay, but some other kinetic energy form you really don't expect if this is the first time you deal with it. For example, if I tell you an example of kinetic energy is heat, how would you think about this? You go, well, how is heat kinetic energy? Okay. I touched a coffee mug, okay, that I just put my morning coffee in. And I touched the side of it, ouch, burned my fingertip. Okay. And you're telling me now that that hotness, that hot that I felt on the outside of the coffee mug, that's kinetic energy? It doesn't make sense. The coffee cup didn't hit me, it burned me. Okay, I don't see the coffee cup moving at me. Okay, and you're right. You didn't see the mug move. Okay, but just because of that, you can't deny or disprove that heat is energy of motion. Okay? Okay, so then now convince me, why do you call heat a kinetic energy? Energy of motion, what's moving? Well, molecules, ions, whatever. Yeah. How do you make something hot? Okay, easiest way, okay, put it on a stovetop. Okay, put some flame on it. I'm gonna heat it up. Okay, but what happens during that? Like, let's say you're heating up a pot of water, okay, on the stove. Yeah, and it's getting hot. What exactly happened there? Okay. Yeah. When you start that, okay, yeah, you're putting energy into the pot, okay? But remember, okay, that pot is not just one layer of atoms or ions or whatever, okay? Okay, that pot is probably millions of layers of atoms, okay, separating your stovetop and your water inside. Yeah. How did the energy eventually got to the water and make it boil? Your energy goes into the first layer of the atoms on in your on the side of your pot, okay? What are your atoms and molecules going to do when they get that much energy? Okay, yes, they're solid. They're not gonna, these atoms, these molecules, these ions won't run away, but the extra energy makes them vibrating at their own solid position much faster. Okay? And as the speed of these first layer atoms and molecules start to pick up, they're gonna hit the second layer. Okay? Make that second layer start to vibrating faster. Okay? And then the third layer, the fourth layer, the 1 millionth layer, okay, and eventually that inside layer of your pot, okay, now it starts vibrating and hit on water molecules. And then water molecules would then go on to the next water molecule, okay, transfer energy, transfer speed onto it, and so on and so forth. Eventually, that entire pot is heated up. So you have this pot, let's say, has layers of atoms, molecules, ions, or whatever. So when you heat it up, the kinetic energy transfer from first layer to second layer, third layer to fourth layer to the most inside layer, and eventually it transferred to water molecule inside this pot. Okay, and so heat, which we're actually going to study quite a bunch at the beginning of this chapter, okay, is a kinetic energy. All right, so here's the other type of energy, other category of energy. We call them the potential energy, PE. Okay. Potential energy is stored energy. Okay. And it's not released yet, it's stored somewhere. Okay. For example, for chemical, you would have potential energy stored in its bond. Okay. Now think about explosives. You light it up, boom. Okay. Lots of energy released, destroy buildings or whatever. Now, before you light it up, what's in there? Some chemicals. Okay. The explosive is a chemical. Okay. Or different kind of chemicals. Yeah. Inside there are all kinds of different chemical bonds. And your energy for that explosives is stored in the form of chemical bonds. And then, of course, you light it up, you make a chemical reaction happen. Now, then those stored energy could then be released. Now, so any chemical energy or potential energy. Okay? No. And in our discussion about energy and chemistry, we're going to discuss both the two types of energy, kinetic and potential. Now, we're going to start from the kinetic energy, okay, by studying heat. And then this heat between for one object, different heat transfer between different objects, and then we're going to move on to the chemical energy, energy released or absorbed in a chemical reaction. Now, for right now, we'll conclude our class here. And last lecture, I think, is a little bit longer, a couple minutes longer than it normally is. Well, this one, I'm giving you back the 2 minutes that I took from you watching last video.